everyone, this is Irina Agustin, and in this video I'll be walking you all through my machine learning project, which is the system threat forecaster. The goal of this project is to predict the probability of a system getting infected by various malware based on different properties of the system. This is crucial because early detection of malware infections can help prevent security breaches. So let's first go through the data set. So this data set contains telemetry data collected from antivirus reports, and it has 1 lakh rows and 76 columns for the training data, and for test data it has 10,000 rows. So our first step will be exploratory data analysis, which is basically examining and analyzing the data set so that we can summarize the main characteristics, gain insights from it, or identify patterns, trends, outliers, etc. So here we can go through all the details of each column in the training data set and the test data set. We can see that we have many categorical columns, numerical columns here, the number of not null values here, same for test data. And now we'll be identifying the missing values in our data set so that we can impute or remove them if required in the future. So as we can see that the column with the maximum number of missing values is S mode, and they only have 900 missing values, which is basically 0.98% of the whole data set. So since this is an insignificant number or percentage, we'll be not removing it, but instead we can just impute them in the future. And similarly for the test data set, we can observe them here, and yes, so here we are just looking if the same columns in the train and test data have missing values. So we can see that almost all of the columns with missing values are similar for the training and testing data, just a few of them which are different. Now we'll be analyzing the unique values, the unique value count in each column. So we can see that machine ID has a significantly higher unique value count, which is almost as much as the total number of rows in the training data, which is 1 lakh, and here it's just 100 and something difference. So we can assume that machine ID might be a unique identifier or a primary key for this data set. Since machine ID has a very high cardinality as much as the total number of rows in the data set, it's better to drop them before training. Now we'll be going through the low variance and high variance columns. We have identified these so we have observed from here that just these 5 columns have a significantly higher cardinality, whereas these 3 columns just have one unique value throughout. So it's actually better to drop them. Now, as we saw earlier, yes, the above 3 columns mentioned earlier just have 0 throughout the whole data set. So having them or not may not be that useful. Now let's go and analyze the descriptive statistics for our numerical and categorical features. So you can see the count, mean, median, quartile of every feature in the numerical and categorical type for each feature. Yes, now it's time for us to observe the distribution of the target variable throughout the data set. Here 0 means that for the given properties in the row, in a certain row, has no malware detected, whereas 1 means malware is detected, and thus we can see that the data set distribution is balanced with respect to the target variable, and hence we don't need to do any oversampling or undersampling for handling this data set. Okay, now let's observe our numerical and categorical features. As we can see, we have 28 categorical features and 48 numerical features. Now it's time for us to observe any outliers in this data set. So for that I'll be using the IQR method, which is basically observing if any of the outliers are outside the interquartile range, and and plotting a graph for the most outlier percentage features. So we can see that only 3.98% of the whole data set have outliers. So these three features have majority of the outliers, and these should be handled if we are using linear models and if they have low correlation with the target. Now these features with outliers will be handled by using the capping method. So for now we'll just go through the correlation of different numerical features with the target and between themselves. So over here we have observed that the variable with the feature with the most correlation with the target is number antivirus products installed. Also the antivirus configure ID that we saw earlier with the most outliers, we can see that they have one of the highest correlation with the target, so dropping them won't be a good idea. Now let's go through the now let's observe the correlation with the target in a more detailed manner. So in this heat map we can see that antivirus config ID has the highest positive correlation with the target and the highest negative value is 0.15, and so after going through this heat map we can see that almost all of the features in this data set have weak correlation with the target. So just blindly dropping any of them won't be beneficial, as multiple properties contribute to this malware infection. So we have to be really careful while dealing with features. Now in this map we can also see that even though these systems have system protections, even though this system has security protections like in system protected, that does not mean that they are like completely safe from malware. And also features like these IDs and other features enabled here show that they have negligible correlation with the target, but we'll be like considering of dropping them or not after further analysis. Now we'll be observing the correlation of different numerical features among themselves. So for a better visual analysis, we'll be considering only the highly correlated features with a correlation more than 0.9. So we have three pairs. So here we can observe that they have 0.995 and almost 0.99 correlation among themselves. So these are like highly correlated, and we can observe that among these features one of them have a very low variance and these have almost same variance. Now we'll also observe their feature importance in the future if required, and here we can see that they have a very low correlation with the target variable. Now we might consider dropping one of these features in each pair if required before training. Now as we noted earlier, these are highly correlated, that is, you can see that they almost have a same pattern here. Now our next step will be further feature analysis, that is, we'll be observing the important numerical and categorical features in a very detailed manner. So first we'll start with the univariate analysis of numerical features and then bivariate analysis with the target variable. Yes, so for the numerical feature analysis, we've considered the top features with high correlation with the target. So for now we've filtered features with correlation more than 0.02, and we have 22 features like that. Now we'll be analyzing each of these features and their distribution throughout the data set. As we can see that most of them are highly skewed. They are either right skewed or left skewed, and some of these features are partially balanced. And we can observe that many of them have binary features, like 1 0 here is touch enabled. Yes. Okay. Now this means that since these are like they have like extreme values, so we'll have to handle them in the future using log transformation or cap outliers. We'll see that later. And now it's the time for bivariate analysis on these numerical features with the target. Okay. So here we can observe that number of antivirus products in this data set. Number of antivirus products installed in the system is like comparatively low, just 1 or 2, and the higher values will be just 4 or 5, and these mostly are not affected by malware, whereas some systems have been affected by this malware. And coming to the antivirus configuration ID, they are like evenly distributed, whether if it's like affected by the malware or not. And coming to the other features, we can see that the same here as well, same for them. As well as the other features, we can see that even though their values differ, they all have an equal chance of being affected by the malware or not. The same goes for the others. You can observe that some of these features have outliers. We might need to handle them if we are using any linear model. We'll go for a deeper categorical feature analysis. For the categorical feature analysis, we only consider the columns which have less than 10 unique values, because it will be more easier to visualize and analyze them better. So in total we have 15 features like that. We'll start with the univariate analysis on these categorical features, and we can see that these 3 features in the first row are like highly imbalanced. The same goes for OS version. We have 10 highly dominating the others. And for the count of OS platform sub-release, we have RS4 and RS3 dominating, and Home and Pro for SQ edition. Now the device family is mainly desktop rather than the server. These are like dominating as well. And for the primary disk, we have a few like HDD and SSD, and for power platform role, we have desktop and mobile dominating the others. Also, we can observe that some columns have a value called unknown here. We'll be considering of whether to handle them or not if there are like too many values with that. If required, we'll be like removing or replacing them. So the whole overview is like, for the categorical features, we have like very imbalanced features here, like most of them are very imbalanced, and we have slightly balanced features like the OS platform sub-release, count of OS install type, and very few features like that. And we have a few features with the value called unknown. We'll be analyzing them after this. Yes, and we can see that auto update option name has a very high number of rows with the value unknown. So for that, since the other features don't really have much rows with the value unknown, we'll be like replacing with null, so that these will be imputed in the future. Auto update option names which has a high count of the value unknown won't be handled, because we can consider that as another category. Now coming to the bivariate analysis on categorical features. So this analysis shows that how different categorical features correlate with the malware infection rate. When a defender has a higher malware infection rate compared to MSC, and over here it's like comparatively slightly balanced, I'll say, that compared to the each value in this features. Now we can see that they are like evenly contributing to the malware infection rate, whereas in the infection rate by device family, we can see that Windows desktop has a more malware infection rate. Observe that most of these features have a fairly distributed correlation with the target, and some features like the product name, OS version, the device family, they are like imbalanced. So these are like fairly distributed, and we'll consider dealing with them later. Now let's go to the highly skewed features in the numerical columns of this data set. So we'll be considering, first we'll be like filtering the features with skewness more than 1. Since we are like planning to deal with them later, we'll also observe their correlation with the target on the side. So here we have the features with the highest skewness, and then their correlation with the target as well. And then we'll be, after this analysis, we'll be considering of whether to handle them or transform them in any manner. As said earlier, these are like highly skewed. Here it's right skewed, then left skewed. Some of them are like slightly more distributed. Yes. So my approach was to handle them using log transformation. So for log transformation, we'll only be considering the continuous skewed features, the positive skewed features. So for that, we'll be removing the values with IDs, because it's not reasonable to log transform IDs, and the values which have binary values like 1 or 0, we won't be considering them for log transformation. We won't be also considering features with low skewness or insignificant impact on the model performance. And when features have like really low correlation with the target, they won't be that useful for the model. So after removing or filtering out these features, we have created a list called log transform features with the required features which we'll be transforming. So our next step is feature engineering. In this step, what we're doing is we're transforming this raw data into a more meaningful features, so that this can help us improve the model's performance. So in log transformation, we are like converting these skewed features to a more normalized form, so that it's easier to improve the model's performance. And we filtered them out as we saw earlier, so that only the meaningful transformations were applied in this model before the pre-processing and training step. Now additionally, I've created extra columns from the date columns. So I've created different columns like extracting their month and year, and I've also created columns which tracks down the day since the OS update, the month since the OS update was last done, and I've created a new feature called activated soon, which states whether the system's OS has been updated within the last 30 days or not. This is like created for a more in-depth analysis on the timelines. Now the correlation between the date the malware signature update was done and the OS of the system was last updated, they have a really weak correlation. So we don't have to like interact them or combine them together. Now the date of the signature update has a very high correlation compared to the OS update date. Now I had also checked the last date, the correlation of the newly created features with the target, and observed that the dates since the last OS update has a negative correlation, which means that the outdated systems were more vulnerable to malware infection. And now the activated zone, that is the systems OS which were updated within last 30 days also were slightly prone to the malware infection. Which now I had created functions for seeing the plots of each of these new features. And after creating those graphs, I had observed that The activation ones had more system malware infection during the mid-months, and the newly activated systems was more infection prone, and whereas for the OS installation it remained consistent, whereas slightly old ones were more affected considering the months. These newly created features had a very ambiguous result insights, so I didn't use them for the final best model, and also creating these new features decreased my accuracy, so I'll be continuing without them. Now this was my initial approach for the feature dropping analysis. So what I thought of initially was dropping the features with very low variance, like the ones which had only one unique value throughout the data set, and also the values with high cardinality, like the ones with more than 12,000 unique values. And then since this was my initial approach with both the date columns, newly created date columns, and so I'll be like removing the initial date columns. This initial approach was done while I had created the compared to the newly ones. While I had created the above five features from the date columns, a pair which had it would be better to remove the original date columns among the highly correlated features, and then I had removed the features with the lowest correlation with the target. And even though I did go for an extensive approach for dropping, I realized that this approach wasn't that good since the accuracy decreased, and also, as we had observed earlier, the correlation of all these features were comparatively low for the whole data set. So removing features like this should be like really done carefully. Since the above approach led to a decrease in accuracy, we were just dropping the most irrelevant features, like the features which had only one value throughout the whole data set, that is unique value equal to 1, and the machine ID, which is the unique identifier or primary key of the data set. So we'll be dropping these 4 columns only, and with that now we have 72 columns in total. Our next step is a very important step, that is data preprocessing. So in this step we'll be cleaning, transforming, and preparing data before it can be analyzed or fed into the machine learning algorithm. So for that I've created 2 pipelines, one for the numerical columns and another one for the categorical columns. And then I had created a transformers for each of these pipelines. So what I did inside these pipelines was I first imputed both the features and then did scaling for the numerical features and encoding for the categorical features. So for imputing, so we started the first we started the numerical pipeline. So for imputing, I had used simple imputer, where the missing values, which values equal to null, I had replaced them with the mean of the whole column. And for the scaling of the numerical features, I had used min-max scaler, so that the original features were retained, but they were scaled down to a certain range like 0, 1. So our data set did not have a normalized features, normalized distribution, so I wanted it to be in a range, and most of the features were skewed and imbalanced, so using min-max scaler was a good approach. So okay, now coming to the pipeline for the categorical features, I had imputed it using simple imputer again, and here I had replaced the null values with the most frequent value of each column. Now I had encoded it, as in I had converted the categorical features values, which were object type, and I had converted them into numerical format, because machine learning models can only handle numerical values. So for that I had used ordinal encoding. Even though the ideal approach for nominal variables was one-hot encoder or label encoder, I had used ordinal encoder because I'll be using tree models for these for training the data set. And tree models don't assume any ordinal relationship unlike linear models. And also our data set is quite huge, and using one hot encoder for the whole data set will be like computationally expensive, and we cannot afford dropping many features. Also, another way would be using label encoder, but label encoder does not work with pipelines. So, and also I hadn't mentioned any ordering for each feature. So this will actually work like label encoders. So for the categorical and therefore for the categorical columns I had used ordinal encoding, and uh, each category inside a feature will be assigned a integer value. That is how the ordinal encoding works, given that as an order. But since we're using tree models, these ordinal relationships won't be considered. Now I had fit this preprocessor with the for scaling, imputing, and encoding the features. I had fit them to the training data as well as the testing data and transform them. And then comes the most important part, which is training or model building of the dataset. So I had used three models for my project, which was XGBoost, LightGBM, and Categorical. So all of the three models I use for this project are tree models, because our dataset has complex system properties, and tree models don't assume any linear relationships. They can handle non-linear relationships. They can handle outliers, missing values, and they perform very well compared to linear models like logistic regression and LGD classifier in this dataset. So let me start with my first model, which is XGBoost classifier. So this model works very well and is known for its speed and accuracy. It handles missing values, prevents overfitting with its inbuilt regularization both L1 and L2, and this works in the boosting way. So XGBoost classifier is an extreme gradient boost ensembling method. So how this tree model works is like it first uh, initialize the predictions with a simple model like a weak decision tree, and then it adds on new trees sequentially by correcting the previous mistakes of the previous model using learning rate, and then it uses like regularization and early stopping to prevent overfitting. And now the final prediction of the model will be the sum of all the three weighted contributions. So this model handles missing values pretty well, and it works really well with large data sets like ours. So that's the reason I first approached the XGBoost classifier, and it gave a good result of 62.7% accuracy. And now I had thought of doing feature selection using the XGBoost feature importance analysis. That is, tree models like XGBoost gives us feature importance scores by themselves after fitting the model. So from that, I had fit before identifying the most important features. I had filtered out the features with more than correlation of 0.8, and I had removed the duplicates or picked just one of the features among them which had more importance. And after like filtering out that, then I had only considered the features with importance more than 1%, and these features were again fit to the XGB model just to like see whether my model works better with the just with feature selection or without just feature selection. So we had drop 14 columns, and then finally we just have 30 columns. But we can see that the XGBoost classifier model works better without feature selection. That is, there's a 2% variation here, and the features selected by this model were given here with signature version with a significant um, importance. Now, since the model worked better without feature selection, we'll be like tuning it without it as well. So after tuning, we had received a validation set accuracy of 63.47, which is much better than the original model. and we found out that the best parameters after random search CV was these. Now, randomized search CV was used for the hyperparameter tuning because since our dataset is quite large, using grid search will be very computationally expensive. So random search CV was the better approach, and it also gave a good score as well. Now our second model is LightGBM classifier. This tree model works similar to XGBoost, but it is much faster and uses less memory. And instead of growing level wise, here the trees grow leaf wise, and here the LightGBM supports categorical features without encoding. So the scaling purpose was all inbuilt in this model, and it also used histogram techniques to split faster than XGBoost. After fitting the model, we got an accuracy of 63, and then similarly we had done feature selection for LightGBM as well. And after feature selection, we have observed that the accuracy has reduced, and since we can conclude that this model as well worked better without feature selection, and hence we'll be doing the hyperparameter tuning without feature selection. And after that, we have observed that the validation set accuracy is 63.4%, which is slightly lower than XGBoost. And the best parameters here given here as well. And our third model is random forest classifier. So this is a bagging based ensemble learning method, and this method is robust and easy to tune, and it's less prone to overfitting. So how this model works is that it first creates multiple random data sets using bootstrapping method, and then it trains a decision tree. It is trained using the random subset of features at each split, and the predictions of these trees are done independently, and the final the result will be the predictions using majority voting, since this is a classification method. And this method reduces variance and overfitting compared to a single decision tree. That's the reason we are using random forest, especially for a large data set like ours. Now, in coming to the accuracy, we have observed that the random forest classifier accuracy is 62.74, but after feature selection, it had reduced again. So we can see that feature selection won't be a very ideal approach in our data set. Also because many of the features contribute weakly towards the overall malware infection rate. So using not removing any of the features while training will be a better approach. Hence we are using all of the features here, and again we had done hyperparameter tuning for random forest, and we got an accuracy of 63.08%, which is much higher than the initial model. And now we'll be comparing the three models we trained, and after that we can observe that XGBoost has a comparatively high accuracy of 63.47 validation accuracy, and after submission I had got an accuracy of, on the test data I had received an accuracy of 63.9% in the XGBoost. So we can conclude that our best model is XGBoost after tuning, and because of that we'll be submitting the final best model after hyperparameter tuning, which gave us 63.9%, which is XGBoost. And let's go through how the hyperparameter tuning and the fitting of this model is done before submission. So since this is the final best model, I'll be explaining each and every step. So first we'll be importing the required libraries, then we'll be initializing the XGBoost classifier model here, and to ensure reproducibility of the results, we have set the random state to 42, and to prevent errors due to the default label encoding technique, we have set it to false. And we have set the evaluation metric to log loss, since it's a really good evaluation metric for classifier models. So this evaluation metric checks whether the predicted value and the actual value. It measures the difference between them. Now we'll go through the parameter grid for all the parameter distributions for this model. So we have the number of estimators or the number of trees required for the boosting rounds. So more trees will be good, but it might increase the computation time. Now the learning rate is the step size shrinkage, or how much the current model is like adjusted. So next will be the maximum depth of the tree. So a more deeper tree actually learns more from the data, so that'd be good, but making it too large will cause overfitting. Now minimum child weight is the sum of instant weights needed in a child node. Now the subsample is the fraction of the training data set used per tree. This is to like avoid overfitting again. Now the column sample by tree is the fraction of features used per tree. Now this is just for randomness. Now we are going to initialize the randomized search CV for the hyperparameter tuning. So we have the model here, which was XGBoost classifier, and the parameter gives as well, parameter distributions as well. Now the number of iterations is set to 20. It's basically the number of different combinations to try, or it picks randomly 20 different sets of these hyperparameter. Now I've set the evaluation metric of the scoring method as accuracy here, and we'll be using threefold cross validation. That is, we'll be training on 2 of the folds and testing on 1, and it keeps rotating. And again, we have set the random state to 42 for reproducibility, and the number of jobs equal to -1 means that we'll be using all of the CPU cores. And the error, if we have any error in like while tuning it, we'll just raise it. That's why we have given this error score raise. What our random search CV does is it tries randomly 20 different combined set of hyperparameters, unlike grid search. So this is more faster when it comes to a larger data set, whereas grid search might be more ideal, but it takes a lot of time. And now finally we fit it to the data pre-processed training data, and from that we can find the best estimators, and this best estimators after random search is again used for predicting, and from that we get the accuracy score of the best model and the confusion metric classification report as well. And to check the overfitting in the model, we have compared the training accuracy and validation accuracy. We can see that it's just slightly different, so that means our model is not overfitting and it gives a decent score. And after that we have submitted the test data predicted from the validation set, and we have submitted that, and we have received a score of 63.9% accuracy. So for this project I had used Python packages like pandas for the data processing. For the EDA part I had used matplotlib, cbond for plotting graphs, and then for the data transformation I had used NumPy, log1p, and for the pre-processing, feature engineering, and model building part, and the hyperparameter tuning I had used Scikit's sklearn, and for the models XGBoost and LightGBM I had used their respective libraries. And this model helps detect malware infections early in the systems using data pre-processed and fine-tuned tree models for better accuracy. So that's it. Thank you so much for watching.